So now we're going to move on to another concept, which is how to find the empirical formulas of the compound that you are working with. So let's start by defining empirical formula. What is an empirical formula? Well, it is the basic ratio that gives you the lowest whole number ratio of the atoms of the elements in that compound. So again, it is the basic ratio that gives you the lowest whole number ratio of the atoms of the element in the compound. The empirical formula of a compound shows the smallest whole number ratio of the atoms in a compound. So I want you guys to write down this definition. If it's too small up in the screen, you should have your books open into section 3, and you should be able to find the definition of empirical formula there. So here you go. So why is it important to find the empirical formula? Because we need the empirical formula to actually get the molecular formula. So this is a step-by-step concept. So we did the percent composition for a reason. You need the percent composition to find the empirical formula. You need the empirical formula to find the molecular formula. So how do we find out the empirical formula of a compound? So I'm going to do an example first, then I will let you guys do a problem so that you can apply what you are learning. A compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. It's asking you, what is the empirical formula of the compound? So again, when you're given a question, the first thing that you need to ask is, what is this question asking you for? So you know that this question is asking you for the empirical formula. The second thing that you need to do is write down everything that you are given. You're given that you have 25.9% nitrogen and 74.1% oxygen. So I will write that down, right? And this is what I know, and that is what I'm looking for. So I'm looking for the percent composition of nitrogen and oxygen compound. So the first thing that I'm going to do is literally take that 25.9% nitrogen and just turn that percent into grams. Why am I doing that? Well, I'm assuming that if you have 100 grams of the nitrogen oxide compound, then 25.9% of that is 25.9 grams. And I will do the same thing for the oxygen. I will turn that 74.1% of oxygen into 74.1 grams of oxygen. So as you can see, that's what I did there. 25.9 grams of nitrogen, 74.1 grams of oxygen. But I don't want grams. I'm looking for an empirical formula. In an empirical formula, you need moles. So how do I convert that grams into moles? Well, I'm going to look at my cheat sheet and look at the mole map that you have from mass to mole. You know that the first conversion should be 1 mole over the molar mass of what you're working with. So I'm working with nitrogen here, and a nitrogen weighs 14.0 grams, and that's where I've gotten that 14.0 grams in the first conversion. And oxygen is 16.0 grams. That's where I've gotten that 16.0 grams and the bottom there. So as you guys can see, the gram unit will cancel out. I'm left with the mole. All I have to do is do the math. So I'm going to go 25.9 times 1 divided by 14.0 grams. I will be left with 1.85 moles of nitrogen. I will do the same thing for oxygen. I will go 74.1 times 1 divide by 16.0, and I get 4.63. So the next step after I've converted that percent into grams and that grams into moles is I'm going to look at my two products. I have 1.85 here and 4.63 here. Do you guys see that? 4.63 and 1.85 right here. I'm going to pick the smallest mole that I have. Right? In this case, 1.85 is the smallest mole that I have. And I will divide both the products that I get by that mole. So what I mean by that, so again, I'm going to divide 1.85 moles of nitrogen to 1.85 because that's the smallest, and that will give me a whole number 1 mole of nitrogen. So if I do that for 4.63 divided by 1.85, I get 2.50 moles of oxygen. So in this case, when you have a formula, you know that you cannot have a non-whole number. Like this will not work. N 1.85, O 4.63 doesn't work. But so that's why we are dividing everything by the lowest mole that we've gotten first. But as you guys can see, it works for nitrogen because a number divided by itself will give you 1. But in this case, 4.63 divided by 1.85 gives you a non-whole number still. So that means that I need to do one more step so that both my moles will be a whole number. So what should I do? Well, the easiest thing to do would be to just look at it and say, well, if I multiply both my moles by a certain number, can I turn that into a whole number? Well, yeah. So if I look at 2.5, if I multiply that by 2, I know that I would get a whole number, which is 5. Right? So that's what I'm going to do. So I'm going to go, well, whatever I do for one, I have to do to both. Since I multiplied 2.5 by 2, I need to multiply 1 mole of nitrogen by 2 also. So that means that I have 2 moles of nitrogen and 5 moles of oxygen. Good? Because again, we can't have that non-whole number down here. They all have to be a whole number. Again, lowest whole number ratio is what empirical formula tells you. So in this case, I have 2 moles of nitrogen and 5 moles of oxygen. So the formula will be N2O5. Does that make sense? Hopefully it does. So here's an example of a problem that you can do. Let's start with letter A. So I'll give you guys some time. I'll ask the teacher again to pause the video. Then if once everyone is done talking to your partner, again, help each other out, then the teacher will play the video again, and hopefully the results that I get is the same as the result that you've gotten. So pause real quick. Good? So the first thing that you should do is turn that percentage into a gram unit, because you can turn that gram unit into the mole unit that we do need for the empirical formula. So the first thing that you need to do is go 94.1% and turn that into grams. So it's going to turn into 94.1 grams of oxygen, and that 5.9% of hydrogen will now be 5.9 grams of hydrogen. The next step would be to turn that grams into mole. So that means that we need to find the mass of oxygen and the mass of hydrogen. The mass of oxygen in the periodic table, if we round it to the nearest tenth, is 16.0 grams. And the mass of hydrogen, if we round it to the nearest tenth, is 1.0 grams. So what I'm going to do is go 94.1 grams. Then my first conversion would be 1 mole of oxygen is about 16.0 grams, right? This would give me moles. I know that I have 5.88 moles of oxygen when I do this math. This gives me 5.88 moles of oxygen. Next, I'm going to go 5.9 grams of hydrogen times 1 mole of hydrogen, and the mass of hydrogen is 1.0 grams. And you know that 5.9 times 1 divided by 1 is the same thing. It's 5.9. So I have 5.9 moles of hydrogen. So again, I have 5.9 moles of hydrogen. So I'm going to look at the 2 moles that I have. I have 5.88 here and 5.9 here. The smallest one I have is 5.88. So I'm going to use that to divide the 2 moles that I have so that I can get at least one of them to be a whole number. So I'm going to go 5.88 divided by 5.88. That should give me 1. Then I have 5.9 divided by 5.88. When I do that, I get 1.003. So that is close enough. If you're 0.003 off to 1, then I would just round it to the nearest tenth and you get 1. So it's the same thing. So you have a 1-to-1 ratio. Empirical formula for that first one should be just OH. So it's literally almost a 1-to-1 ratio because the number that you get when you divide 5.9 to 5.88 is 1.003. So instead of me multiplying both numbers by thousands, I'm just going to round that 1.003 to 1, and that gives me a 1-to-1 ratio. So again, it should give me the empirical formula of OH. So if you're working on B, you have 3 components here. You have mercury, sulfur, and oxygen. So you need to find the empirical formula of each compound. So that means that I need to turn that 67.6% of mercury into 67.6 grams of mercury, that 10.8% of sulfur into 10.8 grams of sulfur, and that 21.6% of oxygen into 21.6 grams of oxygen. So I'm going to start with mercury first and convert that 67.6 grams of mercury into moles of mercury. So I'm going to start with 67.6 grams. I need to find the mass of mercury. So if you're looking for mercury, you know that it is a transition metal, atomic number 80. So if you look at the mass, it's 200.6. 200.6, 1 mole of mercury. So when you do the math, you go 67.6 grams times 1 mole divided by 200.6. You get 0.337 because you have 3 significant figures. So 0.337. 0.337 moles of mercury. Now I'm going to deal with the sulfur. So I have 10.8 grams. I have 10.8 grams of sulfur. I need to find the mass of sulfur. So 1 mole of sulfur, the mass of that is 32.1 grams sulfur. So when I do the math, I'm going to go 10.8 divided by 32.1. I get 0.336. So again, I get 0.336 moles of sulfur. Good. So 0.336 moles of sulfur. Now, I have to deal with the last one, which is oxygen. Oxygen is 16 grams. So I'm going to go 21.6 grams of oxygen, 1 mole, 16.0 grams right here of oxygen. That should give me, if I do the math, 21.6 divided by 16 gives me 1.35 moles of oxygen. Again, I get 1.35 moles of oxygen. So I picked the least. Again, 0.337 and 0.336, that's close enough. So I go 0.337 divided by 0.336. I get 1.00297,619. But then again, like what I said, instead of me multiplying that to a gazillion numbers, I'm just going to round that to 1. Then 0.336 divided by 0.336 gives me 1. So far I have 1 mercury, 1 sulfur. So the only thing is figuring out the oxygen. So I go 1.35 divided by 0.336. I get 4.017. Again, it's close enough, just round it to the nearest whole. That should be about 4 oxygen. So the empirical formula for letter B should be Hg1. You don't have to write it down. So S, which is also 1, so I don't have to write it down. And O, I have 4 of them. So again, the empirical formula should be HgSO4.